Yes, yeah.
And you received a PhD working at the Inter-University Center
Astronomy and
Physics
astronomy.
working on semi-classical gravity and thermodynamics
Yeah.
for ISIS.
Yeah.
Then you went for a postdoc to Canada to
Yes.
help me with the university.
New Brunswick. Yeah.
And working on quantum gravity, and from there you
Came,
masters
yes.
and working on many things that we are interested here as well. Also beyond what we do, like a black hole information parameters. But today you're going to talk about using quantum probes and Unruh-deWitt detectors
Yeah.
for probing spacetime.
Yeah.
Thank you very much.
Thanks a lot. So, thanks first of all to Professor Bruckner for hosting me here, okay, and for the kind introduction. So, as he already mentioned, I will be speaking about quantum probes, curvature and small scale structure of space-time. That is a deliberately very broad theme of the talk that I have given. I hope that the subtitle which I have listed here is basically the point I want to drive home, and this is slightly more specific, and by the end of the talk I hope that it will be clear that what I am really advertising is that there are tools which have already been known in conventional differential geometry for a long time, but not usually used, related to non-local bi-tensors such as Synge's world function, Van Vleck determinant and stuff like that, which can be used to characterize behavior of, for example, quantum probes like Unruh-deWitt detectors, and also the small scale structure of space-time. So, I will cover a broad arena. I will try to start by presenting a couple of specific results, where tools based on these objects play a crucial role, and then I will apply this to a formalism which we have been developing for a few years now, and see what this has to say about the small scale structure of space-time. So, that is the plan of the talk. I will first talk about classical clocks and quantum probes, like I already mentioned, Unruh-deWitt detectors in curved space-time. I will then go to a unrelated, though not very unrelated, but apparently disconnected topic of generalized uncertainty principle. The connection is because the same set of mathematical tools that we will encounter in the first part will come also in the second part. The idea behind all of these efforts is to incorporate or ask what is the role of space-time curvature in these well-known results, quantum as well as classical. And finally, depending on how much time we are left with, I will describe how one can go beyond a given fixed classical background geometry and say something about quantum space-time using exactly the same sort of tools without wandering too far away from conventional differential geometry. Okay. So, let me start. Let me first fix the domain in which I am going to speak about. That is the domain of quantum field theory in curved space-time, semi-classical gravity, but slightly away from semi-classical. It is not full quantum gravity, it is not completely semi-classical gravity, but it is what I will call as a mesoscopic domain, a domain between semi-classical gravity and quantum gravity, specifically important for the last part of the talk, and I will probably come back to it again when I go to the last part. Okay. So, and these will be the key themes. This is what I will discuss first, that is essentially the structure of quantum vacuum in presence of space-time curvature. Okay. I will indicate how space-time curvature can affect some known results like the Unruh effect or the Unruh temperature non-perturbatively. This is something I am not going to be speaking about, but actually one of the upshots of all this work would be to provide support for what is called as an emergent gravity paradigm. Okay. That will not be the focus of my talk, but I thought I will just mention it in the beginning. And finally, the small scale structure of space-time, which is, as I said, is the last part of the talk. So, let me begin with the first one, and what essentially will be the focus here is going back and revisiting the role of accelerated frames, but not in Minkowski space-time like we know it, in an arbitrary curved space-time. So, a problem which is very straightforward and simple to state, but I will tell you a result which says that you can still bring a fresh perspective on this problem, the motion of accelerated systems in a curved space-time. by actually showing that a large set, an infinite number of specific type of Riemann tensor terms can be exactly summed in describing the dynamics of accelerated systems. And that is obviously important for things like principle of equivalence, Unruh effect, like I will say, and some other conceptual issues like Mach principle and the origin of inertia. Okay. I will speak about only the last one, but it is obvious that it has implications for all the other ones as well. Okay. And in GR, one usually assumes that rather, if you use the principle of equivalence, usually one assumes that if the length scale associated with acceleration is much smaller than the curvature length scale, one can use the results from Minkowski spacetime, and that is the sense in which one can say that accelerated frames can mimic a gravitational field. Okay. I will try to argue that that's a bit of a tricky statement to make, and I will explain how. Okay. So, I will start with the famous expression for the Unruh temperature. Okay. In the sense that if you put a detector, a simple monopole detector on an accelerated trajectory in flat space time, Unruh-deWitt, Fulling, Davis and all these guys showed that it will behave, or its response will be as if it sees a temperature which is given by this. Okay. I want to put the same guy in a curved space time and see how curvature affects it. The first thing that comes from intuition is to work out the perturbative corrections term by term in curvature, but that is not what we are going to be interested in. There is a non-perturbative effect, which is what I want to demonstrate. Before I jump there, I should mention that there is a classical version of the same result which is not disconnected from the Unruh effect, and that is your twin paradox. Okay. If you have twins, one of which is accelerated, one of which is moving on an inertial trajectory, the relation between the proper times measured by these twins is this textbook expression, which is often used to discuss twin paradox. Even this relation gets affected by the presence of background curvature. So, I am going to revisit this elementary fact as well, and the same difference which curvature causes to this result will also affect the response of Unruh-deWitt detector. The connection is purely mathematical, but not very unexpected, as I will show. So, let me go and directly describe the formalism. This is your accelerated detector in a curved, arbitrary curved background, and you take any 2 points. The first sort of boring mathematical calculation I want to do is what is the relation between the proper length or proper time between these 2 points on the curve and the geodesic which connects the same 2 points. Okay. That lies at the heart of the whole calculation. So, basically that quantity, the square of the geodesic distance, is what is called as the Synge world function apart from a factor of 2. It is something I will denote by sigma square, will play a key role in rest of the talk. Okay. So, if you take 2 points on the trajectory, ask what is sigma square, I want to replace the dependence on trajectory with the dependence on curvature. Okay. And that is where the non-trivial result will come from. Okay. So, let me begin, and the first crucial input I will use is to describe the geometry in some manner, suitable approximations, but of course, at some point those approximations will break down. So, let me explain what these are. So, I am going to assume that the curvature in this whole region, it may be large, but its derivatives are small. So, what I will do is keep all terms involving the Riemann tensor, but ignore all terms involving covariant derivatives of Riemann tensor. So, the first covariant derivative, second, third, all those things will be ignored. Numerically they can be computed, but analytically their contributions cannot be summed. It will become clear later on. So, what I have just displayed for, what I have just displayed for you here, just to set your intuition straight, is essentially a fully summed up version of Riemann normal coordinates. So, if you look at Riemann normal coordinates, that is just the first term in this series, eta ab plus 1 by 3 Riemann tensor times x a x b. That is how you describe approximation, a flat space time approximation of a curved space time. The first curvature correction is 1 by 3 R A B x A x b. That is the k equal to 1 term in this series. But you can show that if you ignore the derivatives of Riemann, all the remaining Riemann terms can be neatly written in this combinatorial form. Okay. And now it is the second aspect. This was about how I am going to describe the metric. Now, how I am going to describe the trajectory itself. So, I told you that I am going to consider a version of uniformly accelerated detector or a particle or a frame. which in flat space-time would satisfy these conditions. And in curved space-time, similar conditions well motivated by the standard Serre-Frenet expressions from analytical geometry were given by Rindler very long time back. So, the idea is you take the Fermi derivative of the tangent vector on the trajectory, set it equal to 0, and that will give you these conditions for hyperbolic curves in curved space-time. Okay. If you do it in Minkowski space-time, you will get hyperbolas, that is the known result, but this is a generalization of those in an arbitrary curved space-time, it is covariant generalization of those. So, now the thing is very clear, I know these conditions, I know the metric from which I can compute the covariant derivatives, and then I need to compute this relation between geodesic length and the proper time. Okay. That computation, this is just to give a scary feeling of the kind of calculation involved, I am not going to argue about any of the terms. So, you can plug all of these conditions in a package like Cadabra, make it run for a long time, and it gives you a nasty expression like this. What I want to highlight is that there is a peculiar structure hiding in this expression. There are complicated Riemann tensor terms being summed over all different combination of indices, but what if you stare hard enough, and it took us a long time to stare at this expression, there are certain terms which are underlined in red, which involve what is called as the electric part of Riemann, that is the sectional curvature of the plane of motion involving the u, which is the 4 velocity of the accelerated curve, and n, which is the direction of acceleration, that is a spatial direction. So, u and n are orthogonal unit vectors. So, this component of curvature appears in a lot of terms, and if you just stare hard enough, and the paper explains it in detail, which I am not going to go through it, you can show that all those terms sum up to this analytic expression. Okay. It is not simple, but certainly simpler than the infinite series that comes out of a numerical package, and that is an extremely interesting result. This is actually the result we are after. The remainder term here are all the terms involving the components of Riemann tensor which are out of the plane of motion. So, if the acceleration is in a specific direction, the 4 velocity and the acceleration will form a plane. All components of Riemann of that plane are here, they cannot be summed, at least we could not sum these terms, but I will show that in many interesting situations those terms are actually 0 by symmetry. Okay. So, this is the crucial expression, and that is it, we are actually done with the key result. So, let me indicate a few limits of this expression. If you take the curvature going to 0 limit, what happens in Minkowski space time, you can show that this expression reduces to the Rindler expression that we are all familiar with. Okay. That is the Rindler expression which gave you the twin paradox result, the relation between proper time as measured by a inertial twin versus the accelerated twin. That is also the result which effectively gives you Unruh effect, because the periodicity in the Euclidean accelerated time is what gives you the Unruh temperature. Okay. That is precisely what changes here. If you look at this expression, that expression also has a periodicity in Euclidean time, because if I take tau to I tau, this is definitely periodic. This periodicity will now give you a temperature which is modified in a non-perturbative manner from its flat space time result, that is from the Unruh effect. Okay. And this is very obvious when I write it like this, but let me be a bit more specific. If you read off the inverse of the periodicity as temperature, that is the usual rule, the periodicity in Euclidean time is inverse temperature, it is beta, which is 1 over kT, then this is what you will get for the Unruh temperature. Of course, there is a plus all the non-thermal part, but the thermal part of the Unruh-deWitt detector response will get non-perturbative corrections, which is square root. The square root itself is non-trivial, because just a series expansion term by term in curvature would not have given you this. If you were not able to sum up the series, you could not have guessed this expression. But otherwise, it has all the, so this is just forget about this slide. What I am indicating here is that you can repeat the standard calculation of Unruh-deWitt detector response by plugging in the expression for sigma square, which is essentially this expression, square of this is sigma square. You can use the standard calculation of Unruh-deWitt detector response, that is the Whiteman function. You plug it in to the detector response expression, and you can show that the residues are all unity at the poles are at the right locations and all of them. Okay. Those are the details, but you will get the thermal part which is given by this. Okay. Now, in de Sitter, I am talking about any arbitrary curved space time. So, I might as well consider de Sitter as an interesting limit. In de Sitter, I can show that all the extra terms, the approximation ones, are actually 0 by symmetry, and you get a result which is essentially equivalent to the well known Deezer-Levin result, that is the GEMS approach. You put an accelerated detector in de Sitter, that is the temperature it will see, effect of cosmological constant. Okay. So, that is a good check. This is also equal to the extra terms which spoil the thermal behavior are also 0 for several other spacetimes of physical significance like spherically symmetric spacetimes, FLRW spacetimes, in which the expressions are given by this. So, if you put an accelerated detector in an expanding universe, expanding or contracting FRW universe, you will get A double dot by A as the correction to the Unruh temperature. Okay. Similarly, if you do it in Schwarzschild spacetime, and this is more interesting, usually you just naively apply equivalence principle and say that a static detector in Schwarzschild would just see a temperature h bar A by 2 pi, where A is the acceleration of the static detector. Okay. But this actually tells you that even that is going to be corrected by the presence of Riemannian curvature. Okay. So, sorry, it's not. It's actually not the Tolman effect. Yes, we tried to see whether there is a link with the Tolman effect, and that's still an ongoing work. Okay, whether the square root of G00 captures all these terms, but so far we have not found a connection with Tolman. It's not the Tolman effect. So, yeah, this ends the first part of the talk. What I have just described is
Tolman is not curvature. Tolman is not.
it's not. Yes, Tolman is not curvature, but still, if you do an expansion in curvature and just say that square root of minus G00 is what is capturing the redshift, then at a point all the Riemann tensor terms will give you 0 contribution if you put a origin at the location of your detector. So, only Riemann tensor terms that can come out of Tolman effect are terms of the form RABCD XB XD, that is Riemann tensor multiplied by some kind of a size of the detector, finite size, but this is still a point detector, and that is why I am claiming that this has implications for equivalence principle, because it is not a finite size effect. Even for a point detector, that Riemann tensor term will stay there and contribute. Okay. If it was multiplied by size of the detector, I would not be so worried about the equivalence principle, because then I have another length scale to play around with. That is not what is happening. Okay. So, these are some of the implications, but I think I can come back to it again. I have a couple of other results to describe, again using the same set of tools. So, this was essentially the result I have just described has conceptual implications and also the implications about using the right set of tools, which is you take the Synge world function, you have a covariant expansion for it either using numerical package or some analytical insights, and it gives you that nice result. The second place I am going to consider the role of curvature in the quantum dynamics of system is this approach of generalized uncertainty principle. So, let me discuss it. I again want to capture how curvature affects the standard position momentum commutation relationships, either the curvature in space time or curvature in momentum space, which is something I will be more interested in. Okay. So, we know about generalized uncertainty principle. Usually these are models which are speculated to come from variety of quantum gravity arguments, and there are large number of models. I am not an expert and not aware of all the possible models, but I am very sure that there are more in the list here. Okay. So, usually they modify the right hand side of Heisenberg commutators by momentum dependent terms. Okay. So, what we try to do is lay down a formalism in which the right hand side of this modified commutator relation comes from background geometry and its curvature, rather than being put in by hand phenomenologically and motivated phenomenologically. So, that is the motivation. Okay. So, But we don't really believe that just doing quantum mechanics on a curved space or a curved space-time, I can do a particle on a sphere. I don't expect Heisenberg algebra to get modified just because the space or the space-time is curved, although that can be done. But you can show that if you want your momentum operator to be symmetric, self-adjoint, you can absorb all the curvature corrections coming from space-time curvature into the definition of momentum operator. And this work traces back to old work of DAWOOD and other people. Okay. However, your momentum space itself can be curved because of some quantum gravity effects, and I want to express the RHS of this guy in terms of curvature not of space-time but of momentum space. Okay. Basically what I am saying is, if I do not have quantum gravity, if I do not have a length scale associated with quantum gravity, the commutators do not get modified. Okay. So, the only modification has to come from some quantum gravity effects, or they are not there, and I want to fix a final form of this. Okay. So, how am I doing on time? Okay. Yeah. So, again the same set of tools. This is once again the mathematical slide which I am going to use. So, the key tool I am going to use is the following. I am going to use the language of bi-tensors. So, let me quickly describe the Synge world function which I have already mentioned before, but now in slightly more detail. So, like I said, given 2 points on a manifold, assuming they are connected by a unique geodesic. So, this is what is called as a geodesically convex normal neighborhood. Then 1/2 of the square of geodesic distance between the 2 points is what is called as the Synge world function, and it's an object which is a bi-tensor, so that it behaves like a tensor at each of the points. So, it depends non-local, it's a non-local object depending on 2 points, behaves like a tensor at each of the points. Okay. The nice thing about this guy is that you can take coincidence limit of world function and recover or retrieve the information about metric, curvature, everything just from the world function. This is a fact which will play a very important role in the last part of my talk. Okay. So, I will be trying to rebuild the geometry of space-time not by looking at metric tensor, but by looking at the world function. That comes at as the last part of the talk. But for now, let me just go back to my generalized uncertainty principle. Okay. That is the first object. The second object I am interested in is the Van Vleck determinant. This is the guy that goes and sits in the numerator of the Weitmann function or any of the Green's function, the Feynman propagator or the Weitmann function, positive or negative frequency. The numerator, the Hadamard parametrics has a numerator which is determined by Van Vleck determinant. Very easy to understand what that object is. You take any point of a manifold, send out a spray of geodesics from that point. The density of geodesics emanating from the point is what is measured by the Van Vleck determinant. It has a formula which will come in one of the slides, but I am just trying to give you a feel of what that object measures. So, you send out multiple geodesics from the point and measure the spread at a fixed geodesic length from that point P naught. Okay. The density of geodesics which will arise for a given spread here is what is measured by the Van Vleck determinant. There are formal definitions available in standard texts. Okay. So, why have I discussed all this? For the simple reason that I want to study the modifications of my XP commutation relationships, and I want to define my momentum operator as a generator of translation in positions, or the position operator as a generator of shifts in momentum. So, here is how I am going to do it. You take a point P of the manifold, okay, and you again define normal coordinates. These are like Riemann normal coordinates if you have a Riemannian manifold, but in general normal coordinates on any manifold can be defined like this. I am assuming Lorentzian manifold, so there is an eta AB here. What you do is take gradient of the world function, dot it with a suitably chosen tetrad, orthonormal tetrad here, and you define normal coordinates in this manner. I am emphasizing this because I could do it on momentum space, 4-dimensional momentum space, or 4-dimensional position space, does not matter, okay, because this is an abstract definition. Then I shift the origin from P naught to some P naught plus delta P naught, and I want you to compare it with this picture. Okay. Here the shift is active in the sense that a final point is being translated, but to discuss momentum as a generator of translation or vice versa, you usually shift the origin from P naught to P naught plus some delta P naught. So, that is more like a passive point of view, and then you can show that this variation of normal coordinates, which is defined like this, comprises of two terms. One depends on the extrinsic curvature of this surface, and this surface is really the surface formed by the final endpoint of all geodesics which start from P naught and go to a fixed length. So, if I was in flat Euclidean space, for example, then I will start from the origin, send out geodesics of constant length, I will get a sphere. Okay. So, this will be the extrinsic curvature of surface of a sphere in 3 dimensions. All I am discussing is a generalization of that idea. So, the change or the shift in normal coordinate has a term which depends on extrinsic curvature of a surface like this, and a term which has purely normal components, where T A is just a tangent vector to these geodesics. I hope the notation is clear enough for that. Okay. So far it is pure math. I define normal coordinates, I vary the normal coordinates, and I get that expression. But now I say that this shift, the generator of this shift, is what I will define as a momentum operator if this is a position coordinate, or a position operator if this is a momentum coordinate. Okay. So, that is I think I have already mentioned this. I should also mention that this combination is what reduces to Kronecker delta in flat spaces. That is how you recover your standard Heisenberg algebra. So, you recover this delta ij here because this combination is delta ij. Okay. And now I want to apply, so far this was a formalism, I want to apply it to the case where the momentum space is curved. I already mentioned very briefly why I am not interested in the situation where the space time itself is curved, because the curvature of space time affects the definition of a symmetric momentum operator in a very specific manner. One can incorporate it, but that is not what I am interested in, at least in this talk. Okay. Some comments are there in the paper about it. What I am more interested in here is what happens if the geometry of momentum space is curved. Okay. So, we know that in special relativity the 3-dimensional relativistic velocity space is described by the hyperbolic geometry, Lobachevsky geometry, and this can be found in Landau-Lifshitz, for example. This is the 3-dimensional geometry of relativistic velocity space. I want to construct the 4-dimensional version of this, okay, which I will do by demanding that when the relative velocity between two different points in the momentum space is 0, the metric that I want to construct measures the difference in rest masses corresponding to the 2 points. So, my coordinates of momentum space would be the rest mass m and the components of the 4 velocity. So, this is the relativistic velocity space of Landau-Lifshitz, and this is an extension of that geometry to 4 dimensions by demanding that when 2 particles or 2 points in, I should be careful not calling them particles, it is just 2 points in momentum space, do not have any relative velocity with respect to each other. My metric is going to just measure the rest masses. So, it makes physical sense. Okay. And there are some justifications using the center of mass energy of the system and all those things. Okay. So, this is what it is. Now, here what I have done is I have taken into account the fact that quantum gravity might modify the dispersion, the standard dispersion relation. Sorry about this. Yeah. So, quantum gravity might modify the standard dispersion relation between momentum and mass. So, instead of having p square equal to minus m square, if I have a Lorentz invariant deformation of dispersion relation like this, I incorporate it into a formalism by actually setting momentum as not equal to m times 4 velocity, mass times 4 velocity, but some function of mass times 4 velocity. So, that p square is not minus m square, but some function of m square. Okay. This is the only input I am assuming here which some quantum gravity model which is Lorentz invariant will provide. Okay. So, that is an attempt to connect modified dispersion relations with curved momentum space with generalized uncertainty principles. It is a triangle which I will display at the end, but that is the motivation. So, now you can construct a metric using again the identities associated with the world function which I indicated earlier. So, now you construct the world function geodesic lengths in momentum space, take the derivatives of the Synge world function, this is again the Synge world function, but in momentum space, take the coincidence limit, construct the metric, and what you get for the final metric is, so for lack of time I will just go to the final result, it is this. So, here you have momentum space geometry in terms of modified dispersion relation. Okay. if you were working in standard Lorentz invariant quantum field theory where p square equal to minus m square is the dispersion relation described by particle excitations of the theory, then this function f would just be an identity function, and you can show that this reduces to flat space time. Okay. That is the flat momentum space, and I already told you that for all flat spaces the RHS of Heisenberg commutators will be Kronecker delta. So, you recover your standard commutation relation, and that is what I have stated here. But if the dispersion relation is non-trivial, you can write down the Riemannian Ricci scalar of this geometry, and of course, all the other Riemann tensor components, and that gets deformed like this. Okay. So, now you have a curved momentum space. Then you go back, compute the extrinsic curvature, everything, every expression I showed you for the RHS of XP commutators, and what you can show, this is the final result, is that the XP commutators get modifications purely because the dispersion relation of particle excitations were modified from p square equal to minus m square to some function of p square equal to minus m square. That is the standard form in which people study Lorentz invariant dispersion relation. So, this formalism will not apply to Lorentz violating theories. We have actually maintained Lorentz invariance from the start, but as long as that is maintained and the dispersion relations are changed, this is the final result. So, it actually removes lot of ambiguity. These factors here are no longer arbitrary, they are fixed by a single function f of p square, and so is the RHS of the x, even the position, the normal coordinates do not commute. That is the hint towards non-commutative nature of the geometry which will be induced by the quantum effect. So, that is non-zero, and they are completely fixed by just one function f of p square. Here are some forms, but I think I should just move on. So, some very popular Lorentz invariant dispersion relations is what we plotted the RHS of the previous expression for, and this is what these functions basically, this is G1, this whole thing is G2, and that is how it looks like, but I can come back to it later, it is not relevant. So, this part of the talk, what I have tried to do is connect up modified dispersion relations with curved momentum space geometry and the theory of geodesic flows in any curved space, Riemannian, Lorentzian, does not matter, it is indefinite signature. Okay. And that, so far what I have done is analyze probes, quantum probes, Unruh-deWitt detector, generalized uncertainty principle, and try to capture in some manner in a rigorous way the effect of space-time curvature. Okay. Now, I am going to actually go one step further in rest of the talk and ask whether these same set of tools based on world function and Van Vleck determinant can tell me something about the quantum nature of space-time itself. So far the space-time has been classical. Okay. That is the final part of the talk, and it is a work that has been done for several years now, and I am just going to give you a brief flavor of that work in the time which is remaining. So, basically what we are going to ask, one can forget about this part, because as I said, there is a very elegant connection of whatever I am going to speak now with what is called as the emergent gravity paradigm that comes out of thermodynamics of horizons and stuff like that. I will not have time to go into it unless there are questions. But what I am going to do is imagine that there is a length scale that exists in space time in a fundamental manner, which I am going to call as a 0-point length, Planck length if you like, but it could be any length scale, which actually sets a lower bound on measurement of space time intervals. Okay. That was always the motivation behind models like generalized uncertainty principle, but I am just going to take this as a starting axiom. And then one asks whether such a space time which is endowed, quantum space time which is endowed with a 0-point length, can be described with the conventional tools using metric tensor, or you need something else. And I am going to actually push for a point of view that you need non-local differential geometric quantities to describe space time which has an inbuilt 0-point length. Okay. You cannot use metric tensor, Riemann tensor and all those local tensorial objects. Non-local objects like the ones I have been speaking about so far are better candidates. Okay. So, let me go here, and this is something I usually like to show, but for want of time I will skip. This was already actually the intuition for this already was there in the famous lecture by Riemann on hypothesis that lie at the basis of geometry. I have highlighted these comments in bold, but he already was aware that whatever the metrical notions he was describing in his lecture, which laid the foundations of geometry, were applicable in the large, but nothing can be said about its effects in the small, which should come from physics rather than anything else. Okay. So, this is a nice quote which I like to actually display. Okay. Now, because I am going to speak about 0 point length, I should mention some literature on it, and there has been a lot of literature from very old times which actually discuss why space time, why there should be an operational limit on measurement of space time intervals. So, I am just going to skip these references, I can come back to it, but there are some very simple thought experiments. The most famous one being the Saleker-Wigner clock. That is, if you want to assign precise location to events in space time using clocks, there are fundamental constraints that come from general relativity plus quantum mechanics combined, and that bound is essentially set by the Planck scale. Okay. Again, more references. Okay. So, what we do is actually first try to find out a mathematical statement of the fact that there is a 0 point length in space time. So, what we do is we consider again the Synge world function, geodesic distance between 2 points, and we say that a space time, a quantum space time is supposed to have a 0 point length if the geodesic distance between the 2 points does not go to 0 when the points are coincident. So, that is like completely messing up with the standard axioms of metric spaces. Okay. Usually, when the points are coincident, one expects the geodesic distances to go to 0. So, what one is demanding here is a quantum space time should be such that geodesic intervals have a finite limit when the points are coincident. Okay. So, that is the input you are going to put, and this I have already described. This can be very neatly done by taking the Synge world function, computing its covariant derivatives, and moving forward from there. So, here is the philosophy of the work. Instead of metric tensor, you use the distance function, the 2 point function, and I am going to take one step further in the last slide, where I will claim that any 2 point function or correlator or Green's function or propagator is a better candidate to describe the geometry of space time than the metric tensor. So, the key aim is to actually rebuild the metric tensor, Riemann tensor, and all those objects we like from these non-local objects. Okay. So, this again something I have already displayed, so I am not going to spend time on it. So, here are the conditions. What you demand is you construct a metric for which the distance function, which I am going to call as S, calligraphic S, is such that when the points are coincident, that distance function is Planck length squared. So, it is not 0, but it is square of Planck length. That is my definition of existence of 0 point length. Okay. And then the 2 point functions get regularized in the coincidence limit. We know that one of the roles of quantum gravity, that was also then the references I mentioned a while back, is to regulate the UV divergences of quantum field theory. Okay. So, this condition sort of captures that. Okay. Then you once again do your computations. You actually try to find, now it is actually working backwards, you try to find a metric which will have a distance function such that it will satisfy this first condition, and the D'Alembertian constructed using that metric will have a 2 point function which satisfies the second condition. Okay. That is not quite a straightforward or an easy computation, but it just follows from some differential geometric identities. I will directly display the final metric, and that turns out to be this. Okay. So, this is what we call as the qmetric. It turns out to have a part which is conformal to your background metric. Conformal factor is given by that calligraphic function S in this manner. So, sigma square is Synge world function, S is some function of sigma square. We do not care about what that function is, because you need a full quantum gravity theory to know what that function is. All we care about is that at the argument equal to 0, the function will have the value L naught square. So, there is a 0 point length in space time. No other information is required about that function. And then there is a disformal term which depends on the tangent vector connecting the 2 points. There is a non-local object which depends on 2 points. It behaves like a second rank tensor at one point and a scalar at the other point, and this is the structure it has. It is what is called in the literature as the disformal structure. Okay. The most important feature of this effective qmetric is that it is singular in the coincidence limit. That is to be expected because no sensible metric theory of gravity, where distances do not go to 0 when the points are coincident, can be described by a regular metric tensor. So, there has to be some kind of a divergence at the level of metric tensor, but that divergence may not be physical because one needs to compute Riemann tensor, Ricci scalar and all those things from this geometry and see whether they are divergent or not, okay, which is what I am just going to display next. So, you can do that, you can construct the Ricci scalar corresponding to that effective geometry, and that has some really interesting effects which we call as the grin of the Cheshire cat. You construct that Ricci scalar and take the coincidence limit now. First of all, you see that the coincidence limit is finite, but more interestingly you see that when you put Planck length to 0 in this coincidence limit, you get a residual which is not equal to the value of the Ricci scalar corresponding to the background metric. Okay. So, I hope I am making this point clear because it is quite important. What I am saying is that you start with a geometry which reduces to standard metric geometry when L naught equal to 0, but the curvature constructed for that geometry do not reduce to the curvature of the background metric in the limit when Planck length is 0. So, it is almost like the existence of a non-trivial Ricci scalar for the quantum space time is an indication that there was a Planck scale or Planck length in your theory, which does not show up at the zeroth order here, but it modifies completely the form, for example, of the Einstein-Hilbert Lagrangian, because Ricci scalar is just the Einstein-Hilbert Lagrangian. Okay. And that connects very neatly with the emergent gravity paradigm, because this object is often taken as a starting point of a viewpoint in which gravity is treated as thermodynamic in its origin, okay, something that I am not going to discuss in this talk. So, before I end, I want to describe some other implications of this. So, I am summarizing work of several different papers here. So, it might be a bit fast, but I will try to explain. Explaining these things is very simple. So, now that you have this effective qmetric, what we are calling as qmetric, the most elementary textbook level thing that you can do is compute volumes and areas using this qmetric. Okay. So, square root of the determinant of the metric will give you volume, square root of the determinant of induced metric on equal geodesic surface will give you areas and all those things. So, all these calculations are straightforward since you know the specific form of the qmetric, but what is interesting is that if you try to read off the dimension of the effective quantum space time which this qmetric is describing, I am sorry, it turns out that the dimension reduces from 4 at large scales to 2 at very small scales. Okay. So, let me be clear about how I am measuring the dimension here. How I am measuring the dimensions here. So, the dimensions are measured by measuring volume, in the sense that if you measure volume of a sphere, it is 4 by 3 pi r cube in 3 dimensions. So, the exponent of r is what tells you that the space is 3 dimensional. Okay. So, I am using the same logic here, that is formalizing this logic. And this is what happens. You have a 4-dimensional effective description at very large scales, that becomes effectively 2-dimensional at small scales. And support for this has come from various different formalisms of quantum gravity as well. It has been summarized by Karlep in a review, and this seems to suggest that reduction to 2 is a very generic feature of any space time with a 0-point length. Okay. Then there is also implication for causal structure of space time. Light cones constructed using the effective metric seem to shrink at very small scales, and this has connection with the phenomenon which in quantum gravity is often called as asymptotic silence. That is, if you are in the Planckian regime, light cones shrink so that nearby points decouple and they are not okay. Okay. Should I wait or continue? I hope it is not an alarm fire. Okay. Okay. So, yeah, anyway, I only have a few slides remaining. So, that is the second implication, that light cones shrink so that nearby points get decoupled. Okay. And that is very evident from this light cone picture. Okay. Most important implication is for space time singularities. So, we looked at the Raychaudhuri equation and its structure using the effective qmetric, and it shows that the defocusing behavior, or rather the focusing behavior of geodesics gets modified if you actually analyze the expansion and all those parameters which appear in the Raychaudhuri equation using the effective qmetric. Okay. And that has of course implications for the singularity theorems. The version of singularity theorem I like and I am using here is the one by Bourdet, Guth and Vilenkin, the BGV theorem, because that is slightly more general applicability than the Hawking-Ellis version of the singularity theorem. So, that is what I have displayed on this slide. And finally, a broader outlook. So, those were the implications of the qmetric formalism, and just to provide a broader outlook on the results, I am almost done with the talk. We started with analyzing the Unruh-deWitt detector response, or rather accelerated systems in a curved space time, found a non-perturbative correction amongst other terms. There is this interesting non-perturbative corrections which has all the right limits known for space times like de Sitter and all, but it is non-perturbative because you cannot guess it just by keeping a few terms in the power series expansion in curvature. Then we went on to discuss generalized uncertainty principle and found the effect of curvature, but this time the curvature did not come from space time, but from momentum space. And finally, what I tried to argue is that the same set of tools based on Synge world function and the Van Vleck determinant, which helps us get these results, capture the curvature effects in a closed form, can also be extended to quantum space time. You can actually reconstruct quantum space time by just putting one assumption in terms of those bi-tensors, that it has a 0 point length. If you do that, the point of view which emerges is that you can take 2-point function, Green's function or propagator or correlator as I mentioned earlier, or the distance function, construct an effective quantum metric for space time, which in the Planck length going to 0 limit will give you the standard Riemannian geometry, but the moment L naught is non-zero, the geometry or even the effective description in terms of this qmetric will be very much different from the conventional one. Okay. And I hope the example I gave using the Einstein-Hilbert, the Ricci scalar or the Einstein-Hilbert action was illustrative of that, because you get a Ricci tensor when you compute the Ricci scalar of the effective qmetric. Okay. Yeah. So, these are the final summary and future outlook. I think I will just leave it on the slides. Take questions if there are any. Yeah. Yes, yeah.
So in the slide with the minimum length, can you go back to that slide?
Which one?
Where it goes to L square, L0 square.
Okay. This one?
Yeah. So what's the sigma mean again?
Ah, yes. So, sorry, I sort of went fast. The sigma square is the same guy which appeared in the first part of the talk also. It is the square of geodesic distance between 2 points. S of sigma square is geodesic distance between the same 2 points, but measured using an effective quantum metric which we have still not constructed. It has to be constructed from this object. Okay.
Basically, the S of 0 means you consider
coincident points. Yes. So
my general question about these models with minimum distance. So I mean, if you look at 2 points which are kind of close to each other, right? So to distinguish them, it's way harder than looking at points which are far away from each other.
yes.
So if you look at far away points, right? I think it's an educated guess, right? That you can only measure them to a position of the Planck length, right? For far away points. But for close points, you would say, oh no, you can't even get close to Planck.
Yeah. Yes. That is correct. And what you are saying is something that is captured. So once you impose these conditions, the limits that you are just indicating is captured in the behavior of this qmetric, because if your points are very far away, sigma square is very large, then and S of sigma square is a function which goes to sigma square in the limit of last sigma square, so that you don't have deviations. Okay. I am trying to not put any conditions of S of sigma square, because that has to come from some quantum theory of gravity. Okay. But if you just look at the sigma square dependence of this effective qmetric, you can actually show precisely what you are mentioning, that it behaves almost like the GAB itself. The non-locality which is captured in this function goes away. Okay. But if the points are very close to each other, that is what is written here, the QAB is singular in that limit. And then if one wants to talk about curvature or any other properties associated with this effective description, one must first compute derivatives of QAB, second derivatives, compute the curvature, and then take the coincidence limit. Because on the face of it, this guy is obviously divergent, but we are not sure whether it is even the basic guy you should look at. You should consider curvature and its invariants, and then look at their coincidence.
What does it mean when it diverges? Does it mean I can
Yeah, so the sigma square here.
what does it tell me that it diverges at the coincidence?
Well, that does not tell you anything. That is what I am trying to say. So the QAB itself diverging in the coincidence limit does not. All you know is that the geodesic distances measured using QAB will have a bound when sigma square going to 0. Okay. But that comes after you integrate QAB dxa dxb over the geodesic connecting the 2 points. Without the integration, the QAB as an object in itself has a divergent behavior. That's all I mean.
But does it tell you I cannot tell the distance anymore, or
Sorry?
does it mean I cannot measure the distance anymore?
Well, that's a measurement is a different thing. Yes, you may not want to characterize it as a. You can just say that it's a quantum measure of distance, but beyond that, I don't think. I think it's right to say that you cannot measure distances below or close to Planck scales. Okay. I don't know what sense one should even call them distances. Okay. So you are just cutting off something by defining a function which, when the points are coincident, has a finite value. Whether you want to call it as a distance function or not, because it won't satisfy triangle inequality and all those standard properties which a metric distance function should satisfy.
We have some restriction because now there is this other topic.
Ah, okay. Yeah. Sure.
Like 2 weeks before that, but you will be around for the next 2 days.
Yes.
So if
Yeah.
anybody wants to discuss further these things, you will be available.
Yes.
So
I will be here.
So this other talk is Joseph Stefan. This is I want to forget which one is the second. Third talk. Yeah, it's third talk. Yes, that's true.
So
Do you want to join us for this talk?
I think I will join for the talk. If that's not an issue. Yeah.
I think we can leave it like that, doesn't it? Somebody will come.
Okay.
Switch it over.
So I'll just turn this thing off.